Here we have a solubility problem where they're giving us the solubility, they're asking us to find KSP, but it's not as straightforward as dissolving the salt in pure water. Rather, we're dissolving the CeIO33 salt in a solution that already contains a common ion. So this is called the common ion effect. One little note before we begin. There is a polyatomic ion that you may be familiar with, but you may not. Iodate is IO3. Just like chlorate is ClO3 and bromate is BrO3. Let's start by writing a good dissociation equation for the salt. Notice that in order to make the equation balance, we need to have a coefficient 3 in front of iodate. Upon making the ice table, the solid drops out, and the Ce concentration initially is 0, so that will just be a plus X and an X at equilibrium. But here's where things get a little different. We start with 0.2 molar potassium iodate, and conveniently within this salt the assumed subscript for iodate is a 1, so that means that the concentration of the salt is also the initial concentration of the iodate. It's not 0, it's 0.2. But everything else would be the same as before. Note that the coefficient 3 in front of iodate in the dissociation equation means that we need to add 3x in order to get to the equilibrium concentration. So at equilibrium, the iodate concentration would be 0.2 plus 3x. Now let's write an expression for KSP. Make sure you cube the concentration of iodate because it has a coefficient of 3 in the dissociation equation. And if we plug in the equilibrium expressions for the concentrations in terms of x, we get x times the quantity 0.2 plus 3x all cubed. Now we can plug in the information they gave us. They told us at the beginning of the problem that the solubility, that is, the value of x in the ice table, is this particular number, 4.4 times 10 to the negative 8th. So if we know that value, then we can just plug in and solve. (4.4 10 to the negative 8th) is x. And I'd pull out the calculator at this point. Crunch those numbers, and you arrive at 3.5 times 10 to the negative 10th for a value of KSP. And that's what they're asking for. Now, interestingly, what if we had made the mathematical assumption that the value of x is negligible compared to 0.2? In other words, what if we had said at this point, all right, this is roughly equal to x times, instead of writing 0.2 plus 3x, I'm just going to say, it's pretty close to just 0.2. I'd still cube everything. Well, okay, let's plug in the solubility that they gave us, 4.4 10 to the negative 8th, and multiply by 0.2 raised to the 3rd power. And if you crunch that number, guess what? You get the same result as if you had done it a slightly longer way. Not that there's anything wrong with doing it the slightly longer way. It's just that, well, 3 times something on the order of 10 to the negative 8th, when added to 0.2, is pretty darn close to just 0.2. So making the mathematical assumption might save you some time.